Welcome to this lecture. In the last lecture, we were discussing about the decorator pattern. We had said that the decorator pattern is a very important design pattern. If we use this in application development, it gives us a powerful mechanism to structure our application. We can add responsibilities to individual objects as compared to adding responsibilities statically through inheritance. Responsibilities can be added at a time to an object, removed, more responsibilities added, and so on. And the client classes, the client objects, they do not even distinguish a decorated object with a concrete object. The class diagram was simple. We will just recapitulate this class diagram and then I will pose a quiz problem. Please try to do the quiz problem and we will display the solution so that you can compare your answer. Now, let us look at the basic structure of the decorator pattern. In the decorator pattern, the client interacts with the outermost decorator. Both the concrete component and the decorator, they are derived from the component. The component can be an interface or an abstract class, and therefore, the concrete component and the decorator, they support the same operations. But a decorator can add additional operations. There can be various types of decorators, and for those operations which are defined in the concrete component, the decorator for those operations only forwards to the concrete component. On the other hand, for the operations which are defined in the concrete decorator, it executes that and does not forward any calls to the concrete component. And just look at here the cardinality. The cardinality is 1 because at a time to a concrete component we can add one decorator at a time. We can add many decorators, but one at a time. That is the implication here. Now, let us try to solve a quiz problem. The quiz is that we want to write a software using which we can make ice creams. This is a game package, and in this game package we can create ice creams, and we can choose the following types of toppings in any combination in any order. So, we have a basic ice cream, and then we can add toppings to that. We can first have nutty topping, honey topping, fruity topping, and so on. We need to apply the decorator pattern to have this game package written. We want to draw the class diagram and we want to write the Java code. Please draw the class diagram first. Simple application of the decorator pattern. The decorator has a simple structure as you have seen, that the client interacts with the outermost decorator, and the decorator each time contains one more decorator or the concrete object. So, this is the solution. The interface ice cream is implemented by the simple ice cream and the ice cream decorator. The undecorated ice cream or the simple ice cream we have the make ice cream method here, which will draw the ice cream, and then we have various types of decorators here. These are the concrete decorators, and we have the knotty decorator which will add knots, the honey decorator, the fruity decorator, and so on. And each decorator can contain another decorator, single decorator, or the concrete object which is the simple ice cream. So, this is the class structure for this example by applying the decorator pattern. But what about the Java code? Please try to write the Java code for this application, so that we get a feel that how do we really code such a class structure. We need to write the code for ice cream, which is the interface, the simple ice cream, the ice cream decorator, and the concrete decorators. Interface ice cream only has mixed ice cream. I just written here string, it will just print instead of displaying. It instead of displaying a graphic, it will just write in terms of text. Simple ice cream implements ice cream. So, this is the ice cream interface, which is just having the method make ice cream, and then the simple ice cream implements the ice cream interface, and here it just writes basic ice cream. We can have a graphic drawing of the simple ice cream. And then the ice cream decorator, it implements the ice cream interface, and then it has a reference to the special ice cream, and then it takes the special ice cream at the argument and stores the reference to that, because it will pass on the calls to that, and then it has it defines a method. This is the abstract class here. Just see here, this is abstract class ice cream decorator. Basically, this is the class, the ice cream decorator, which is the abstract class, and these are the concrete classes, knotty decorator, honey decorator, and so on. Now, here it defines an abstract method, make ice cream, and it returns special ice cream dot make ice cream. Now, this will be overridden by the concrete classes. Now, the knotty decorator extend the ice cream decorator, which is abstract class, and knotty decorator is a concrete class. It takes special ice cream as an argument. The constructor takes special ice cream as an argument, and then just calls super special ice cream, so that the reference gets stored. And in the make ice cream, it overrides the make ice cream of the ice cream decorator, and then it just add knots, and in the add knots it just prints crunchy nuts, returns crunchy nuts. And the honey decorator is a concrete decorator similar to the knotty decorator. Again, it extends the abstract class ice cream decorator, and then this is the constructor where it stores the reference to the argument that is passed on to it, and then overrides the make ice cream, and then it has only the add honey here, and the add honey is just return sweet honey. So, this is a simple implementation of the example that we have been discussed. Here the decorators only write text but then the actual game, the game package you might want to write in graphics. Those who are inclined programmatically, have done lot of programming using Java Swing and so on, please try to write a graphics based software where using this basic skeletal code you can have the basic ice cream and various types of decorators on it as the player or the user chooses different options. Now, we have some experience on applying decorator pattern. You have seen that it is more flexible than static inheritance. Responsibilities can be added and removed at runtime. We can add a property twice. For example, we can add a double border to a text view, but then in inheritance you cannot do that actually, because you cannot twice, you cannot inherit from a class twice. That will be an error. Adding two borders will be difficult using static inheritance, it will give you an error. And also the decorator, you only add that is needed, and again you can remove those parts, those responsibilities which are no more needed. But using inheritance makes the classes feature laden, lot of features, methods get defined, and many of that you never use also. And also you can use new kinds of decorators independent from the class of objects they extend. But are there any disadvantages with decorators? Yes, we had said that reckless use can make the code very difficult to understand and debug. For example, you might have lot of little objects, 60, 70 or 100 objects, 100 decorators added to a basic class, and these are added in runtime. Trying to analyze the runtime addition of the objects as decorators may make it very frustrating to debug the code. As long as you add only few decorators, these are well within the grasping power of a programmer. But if you add too many decorators, dozens of decorators to a basic object, these appear like little objects getting connected during runtime, makes it very difficult to follow the behavior. Of course, the programmer who has written the code may be easy for him because he has added those lot of decorators and he knows what he has been doing, but somebody else trying to find out what's going on in the code may be very frustrating and hard to learn and debug by anybody other than the programmer who had written the code. So, a word of caution here, if you are using decorators, don't add too many decorators in runtime. We have been discussing the advantage of composition over inheritance in many applications. Both are mechanisms to reuse functionality. In inheritance, we reuse the functionality of the parent class, and these are statically bound and weakens encapsulation. Whereas composition, we again reuse functionality of objects at runtime. This is basically the reuse occurs through delegation invoked through an interface. These are dynamic. Responsibilities get added dynamically, and this is an example of a black box reuse. Just need to call the method of the internal object, whereas if you use inheritance, maybe you can modify the behavior of a method. So, that is a white box reuse using inheritance. Inheritance is a quick way to design new components, just use extends and then it is done. But many programmers make the mistake of using too many inheritance and result in bloated hierarchy. Code becomes difficult to maintain and unnecessary baggage. Many of it has large number of methods, and as for a specific application, the programmer does not even need half of the methods, just uses only few of them. The rest are only unnecessary baggage, just cluttering. On the other hand, composition, the drawback is that if we have too many decorators, it becomes difficult to understand the behavior, because the semantics of interaction are decided at runtime. We have discussed already an important pattern, the decorator pattern. We look at another pattern which is also a very important pattern, the iterator pattern. The iterator pattern, any Java programmer would have already been using the iterators, the Java iterators. But of course, many Java programmers, they do not know why they have been doing it that way. Just because it is there in the book they have been doing, they have not asked the question that why iterators, how does it work, and so on. If we know the iterator design pattern, we will know why you have been using the Java iterators for the collection classes. What is the advantage? For another class which is not part of the collection class or is extended, you have extended from the collection class, how do you define an iterator for that, and so on. If you know the iterator pattern well, not only that, you will understand how the Java iterators work, why you have been doing something in some particular way, what is the advantage, what is the exact mechanism that was used. But also you can use the iterators for a new application. So, it is an important pattern. Traversing of the elements in an aggregation is a very common problem in programming. We do traverse through an aggregation for various purposes. We might like to search something, sort, display all the contents, and so on. The iterators, we know, every Java programmer knows that the iterators provide a uniform way of doing this. When using an iterator, we do not need to know how is the collection implemented, how is a tree implemented. Is it the tree is implemented on a array list, is it implemented on a linked list, and so on. We do not bother, we just use the iterator. Also, for the same aggregate, different client classes may be traversing it concurrently, and synchronization is supported by the iterator class. And even though other methods may be accessing the iterator, still they will be independent, even though different iterations on the same aggregate be occurring, but then these do not impact each other. The intent of the iterator pattern is to provide a way to access the elements of an aggregate object sequentially, and at the same time the programmer need not understand the complexity of the underlying representation. The programmer just calls the methods of the iterator next and so on, The programmer need not look at how is the aggregate represented internally and then find out how to identify the next element, how to identify end of the tree or whatever, the leaf nodes and so on. And therefore, it tremendously reduces the programming effort and makes the code writing easy and understanding the code easy. Instead of having the aggregate object define the way it will be traversed, it is moved to the responsibility of traversing is moved to another class, which is the iterator class. Otherwise, if the iterator, different types of iterators are supported in the same aggregate class. For example, we want to traverse pre-order, post-order, in-order, level order and so on. The aggregate object may become too complex. So, here the responsibility of traversal is shifted to the iterator rather than to the aggregate object. Here we access the aggregate's content sequentially, that is independent of the implementation of the aggregate, whether it is implemented in array list, linked list, hash table, we do not bother. And also whatever be the aggregate, whether it is array list, linked list, hash table, whatever, we have the same interface. All the iterators have the same interface and therefore, it becomes easy for the programmer and also we can use different types of iterators to support different types of traversals on the same aggregate, and also we can have multiple iterators, and each of these iterators, multiple iterators, they do not interfere with the functioning of other. Maybe one iterator is traversing from the front to the end, first element to the last element, and another iterator may be traversing from the last element to the first element. And then if we have created these two iterators, they will not even interfere with each other. The main idea, access elements of an aggregation in some sequential order that is independent of the specific collection. We might define what is level order, and given any tree, we can just have an iterator which does the level order traversal, in order, post order, pre-order traversal and so on. Now, the context of this pattern is that often we need different types of traversal on the same aggregate. We might need multiple iterators by the same client or maybe by different clients, and also all types of traversal cannot be anticipated a priori. We can define the iterators for any specific type of traversal that we need, and we do not want to change the aggregate class. Neither we want the aggregate to have a very bloated interface supporting all possible types of traversals that somebody may need. In the iterator pattern, the basic methods that are supported by the iterator are reset, next, get and has next. The reset, intuitively clear, move to the beginning of the range of elements. Next, advance to the next element. Get, return the value, the current value that is referred to. Has next interrogate to check if there are more elements in the range or we have reached the end of the range. We can have some additional methods for the iterator. Popular methods are remove. The current element may be removed as in the Java list, but it may not be necessary for all types of aggregates. Add an element at the current position, count, return the number of elements in the aggregate, and first, which is basically reset. We will discuss about the class structure of the iterator. We will see how the iterator object is created and how the reference of the aggregate remembered by the iterator, how does the iterator perform the traversal, and how does it implement all these different methods. And then that will help us understand the way the Java iterators for the collection classes work. And also we will try to write iterator for a given class which we have derived from the collection classes for which iterators have not been defined. We are almost at the end of this lecture, and those activities, that is the class structure of the iterator, the code for the iterator, and writing the iterator for a given application, that we will take up in the next class. Thank you.